Hello everyone, and welcome back to Tech Adventure. I hope you're all doing great and staying committed to growing your skills in software development, interview preparation, and embedded systems. In our previous video, we covered the top 50 real C and C++ interview questions. If you missed those videos, I highly recommend checking them out for a solid foundation before moving forward. As promised, we're now moving forward with more key topics like solid principles, design patterns, real-time operating systems, and microcontrollers. Today, we'll be diving into solid principles. Whether you're already familiar with them or just starting out, this session will either refresh your understanding or help you build a solid foundation, perfect for both interview preparation and leveling up your software development skills. If you find this content helpful, like, subscribe, and share to support the channel and help others on their learning journey. Let's dive and continue our topic. What are the solid principles in software design? Can you explain each principle in detail with examples? The solid principles are a set of 5 design principles intended to make software designs more maintainable, flexible, and scalable. Each letter in solid stands for a specific principle. Let's break down each principle with simple explanations and examples. In solid, S stands for the single responsibility principle. Let's see in detail. The single responsibility principle, SRP, states that a class should have only one reason for change, meaning it should have only one job or responsibility. Example, imagine a class that handles both user authentication and logging. This violates the single responsibility principle because it has 2 responsibilities. Instead, you should separate these into 2 classes as shown in example. By breaking down responsibilities, the code base becomes simpler, more modular, reduced complexity, and easier debugging. O stands for Open Closed Principle, OCP. It states that software entities, like classes, modules, functions, etc., should be open for extension but closed for modification. Example, suppose you have a class that draws different shapes. Instead of modifying the class to add new shapes, you can extend it by creating new subclasses. Here, we can add new shapes without modifying existing code. This principle encourages designing software so that new functionality can be added without changing existing code. This is typically achieved through abstraction and polymorphism. By using interfaces or base classes, you can extend the functionality by creating new subclasses. OCP minimizes the risk of breaking existing functionality when adding new features. Promotes the creation of reusable components that can be extended without modification. L stands for Liskov Substitution Principle, LSP. It states that objects of a superclass should be replaceable with objects of a subclass without affecting the correctness of the program. Example, if you have a base class bird and a subclass penguin, the penguin should be able to replace bird without causing issues. However, if bird has a method fly and penguin cannot fly, this violates LSP. Instead, you should design the hierarchy correctly. Better, use interfaces carefully to avoid inappropriate inheritance. LSP guarantees that subclasses can be used in place of base classes without causing errors. Ensures that the system remains stable and behaves as expected. Makes it easier to test subclasses by ensuring they adhere to the behavior of their base classes. I stands for Interface Segregation Principle, ISP. It states that clients should not be forced to depend on interfaces they do not use. This principle advocates for creating smaller, more specific interfaces rather than large, general-purpose ones. This way, clients only need to implement the methods that are relevant to them, leading to more modular and flexible code. Example, if you have a machine interface with methods for printing, scanning, and faxing, a class that only needs to print should not be forced to implement all methods. Instead, split the interface. It allows clients to depend only on the interfaces they need, making the system more flexible. simplifies the design by creating smaller, more focused interfaces, reduces the impact of changes by ensuring that interfaces are specific to the needs of the clients. D stands for Dependency Inversion Principle, DIP. It states that high-level modules should not depend on low-level modules. Both should depend on abstractions. Abstractions should not depend on details. Details should depend on abstractions. This principle promotes the use of interfaces or abstract classes to decouple high-level and low-level modules. By depending on abstractions, you can change the implementation details without affecting the high-level logic. Example: instead of a class directly depending on a concrete implementation, it should depend on an interface or abstract class. DIP is used to reduces the coupling between high-level and low-level modules, making the system more flexible. Makes it easier to test high-level modules by allowing the use of mock implementations. Here's a brief summary of the solid principles. These principles help create robust, maintainable, and scalable software designs. That wraps up our deep dive into the solid principles. Mastering these concepts is key to writing clean, scalable, and maintainable code, and they're often a highlight in technical interviews. If you found this video helpful, don't forget to like, share, and subscribe for more content on software development, interview tips, and embedded systems. Also, I encourage you to subscribe to my other channel. The links are in the description. Stay curious, keep learning, and see you in the next video.